with it for 22 years now.
Something like that.
Make both of us, he's younger than I am, but pretty old. So anyway, he's just pretty old. They just celebrated their 25th anniversary, and University of South Florida, Central Florida, is now celebrating its 50th anniversary this year. So he holds a chair there, and he's received the Pegasus Professor Award. That really makes it sound like you're an old fart.
It does, apparently, when they put wings on you.
The highest award honored from the University of Central Florida. And he's got the APS Edward Boucher Award and other awards. So I'm going to talk to you about ultrafast coherent optical signal processing. I think, as everyone knows, he's kind of the world's expert at mobile lasers and timing jitter and stuff like that. So
Thank you very much. It's really a pleasure to be here because there are so many people on the faculty here at UCSB that I've known over the years, and I've read many of their papers and books. And so while it's not necessarily like a homecoming because I haven't been here, it is truly an honor. So as John mentioned, today I'd like to talk about our ability to develop and utilize these mode-locked lasers so we can generate these stabilized optical frequencies, and we want to use these in applications related to ultrafast coherent signal processing. So what I'd like to do is to give you a little bit of a background for why we're pursuing the approaches that we do with respect to how we make our mode-locked lasers. And then I'd like to talk primarily on two things, some key technologies and some applications. And the key technologies that we're going to try to address today is, one, the light source, which is our stabilized frequency comb source, which is nothing more than a stabilized mode-locked laser. And I'd like to talk about two other interesting technologies which rely on the injection lock properties of VCSELs. And we have one of the world's experts of VCSELs right here in the third row of the audience. And so there is some interesting behavior that I think we can exploit here for some interesting signal processing applications. Then once we have the sort of a light source, a modulator, and a detector, we'd like to see how we can put these things together and utilize them for generating arbitrary waveforms where we can effectively generate waveforms with instantaneous bandwidths of many, many terahertz, but using slow-speed electronics on the order of the rep rate of the laser. That's the arbitrary waveform generation. We'll also show you some interesting techniques on how we can measure these things using what we call multi-heterodyne detection. And finally, I'd like to talk about our ability to use frequency combs for pattern recognition or match filtering, and that could have applications in laser radar or optical code division multiplexing. So the standard mantra here, as many of you already know, diode lasers are great, but what we're trying to do is make mode-locked diode lasers based upon extended fiber-based cavities. Diode lasers have all of the beneficial attributes associated with being small, electrically efficient, no moving parts, super broad bandwidth, which gives you the potential for tunability or the generation of femtosecond optical pulses. But one of the most important things that we're going to talk about today with respect to mode-locked lasers is that you can effectively engineer the cavity Q of one of these mode-locked lasers to be orders of magnitude than what you would think that would be possible with a conventional laser cavity. And hopefully that will be a little bit of a learning moment that I'd be able to share with the audience. And the overall concept that many of you already know and are working on is the ability to have complete photonic integrated chips, which is the electronics, lasers, modulators, detectors, filters, etc., fully functioning on a chip so we can do computing and signal processing at the speed of light. So the typical types of applications that we're interested in with respect to frequency combs might be related towards what I'll call sensing, detecting, and response. So you could envision some kind of two-dimensional semiconductor laser array where each array component could be injection locked with a different component from a frequency comb, allowing you to basically not only steer but generate femtosecond pulses on a particular target for whatever your application is. I don't know, look at the cartoon, use your imagination. Another application is shown here, whereby having independent imaging devices like a satellite, like a Hubble or something similar, these things could be flying about space in some sort of fixed constellation, and the key feature is that you'd be piping timing information and space information between these independent imaging devices. Therefore, this array of telescopes would be something more like a synthetic coherent aperture imaging device where the effective resolution, the imaging resolution, would be proportional to the distance between the satellites, which could be tens to hundreds of kilometers, as opposed to the resolution of an individual aperture. And so for the students, when I take this concept to NSF, I have the telescopes pointing out in space for planetary discovery. When I take this concept and I show it to DARPA, I have it looking down here on the Earth, so the message is know your customer. Another interesting application is basically taking your frequency combs and separating it out with a arrayed waveguide grading router or some other type of spectral disperser, and imparting amplitude and phase information or modulation on a comb-by-comb basis, which would then allow you to synthesize the electric field and perhaps the envelope so you could have exotic radar imaging capabilities. And finally, frequency combs are useful for the three classic modalities of communication: OTDM, which is just basically on-off keying, shown in the center path here, kind of classic DWDM here, where we separate out the individual axial modes, put information on it, and code division multiplexing, where you have on-off keying at one port, but then corrupt the spectrum to generate something that looks like a noise burst. On the receiver end, what you basically want to do is take any two comb components from this laser transmitter, injection lock a passive mode lock laser. This will basically establish a frequency comb which is both temporally and phase coherent with the transmitter. Then this thing can generate a bunch of local oscillators where you can do coherent homodyne or heterodyne detection. It would generate a pulse train of optical pulses here, which you could do all optical switching for OTDM. And basically by impressing the complex conjugate filter shown here as compared to there, you'd be able to do match filtering at the back end. So those are some of the applications we want to talk about. So now, since some of you may or may not be mode lock laser guys, I'd like to have another little learning moment here about this concept of harmonic mode lock lasers. A harmonic mode lock laser is a laser which has multiple pulses in the laser cavity. So what I'm going to show you here is 4 different ways of looking at harmonic mode lock lasers. And the problem is that many times people will say, oh, mode lock lasers are just, pulse trains which are temporally interleaved. And they'll kind of talk about this picture. Or some people will say, oh, mode lock lasers are basically, spectra which are spectrally interleaved, and people try and do a Fourier transformation this way. And clearly, if you do that, you're going to get yourself in trouble. This does not work. So what I'd like to just kind of remind the audience to refresh their memory that a real harmonic mode lock laser is, if you do have pulses in the cavity, where in this case I'm going to interleave 3 pulse sets, this pulse train has a spectrum shown here. This pulse train has the same sort of spectrum shown here. This pulse train has the same spectrum. But because this pulse train is delayed in time, you multiply this spectrum by a phase. Shift in time is multiplied by phase. Classic Fourier analysis. Now the composite output is the sum of the 3. The composite output is the sum of the 3. These different axial mode components may add in phase or not, depending upon the relative phase factor here. And so you're going to get some interesting spectrum on the output here. Whatever it is what it is. Now, the other concept here is you have different axial modes, because if this is an active mode lock laser, you're modulating a frequency comb component, sharing it with its neighbor, which is, a mode locked a modulation frequency array. Now, in this case, I have 3 interleaved spectra, because I've got 3 interleaved pulse trains here. Now, again, since these spectra are shifted in frequency, what this spectrum will transform to is a pulse train shown here. This spectrum will transform to a pulse train shown here. This spectrum will transform to a pulse train shown here. But because these spectra are sort of shifted in frequency, I multiply by a phase here. You add these pulses together, you add these spectra together, and you effectively get some composite spectra. The key feature here, since these are sort of eigenspectra or natural modes of the system, these individual spectra will be multiplied by some sort of coefficient or height, and that at the end of the day, this spectrum and this spectrum had better look the same. And so, just as simple as an example, you can do this for a homework assignment on your computer. What I've done is I've taken 3 spectra and I've interleaved them, and I've chosen the heights to be exactly equal to my previous view graph. So I'm going to take one spectrum shown here, I'm going to call it height 1, another spectrum height 1, and the other spectrum, height 1/2. This is an electric field. So when I put these things together and look at the intensity, here's spectrum 1, here's spectrum 2, and here's spectrum 3. This height is now 1/4. If I add these electric fields up, basically I get sort of sinc squared optical pulses. But notice that these pulses are effectively not symmetric. Notice that there's asymmetry on the wiggles of your sinc squared pulse. And it's this that literally gives rise to what we call supermode jitter. And so, because if you were to try and measure a pulse and ask, where is the center of the pulse, you'd integrate the area under this pulse, and you'd want to compare it to the integrated area under this pulse and compare it to the integrated area under this pulse. Notice this pulse, this thing looks rather symmetric, so its centroid is right here in the center. This pulse, which has more energy behind it, its centroid is not really at the top, but it's effectively lagging. This pulse here, it has some energy in the front, so its centroid is literally leading. So there's effectively periodic jitter in this pulse train. And if we detect this pulse train on a photodetector, here's the RF power spectrum that we'd see. We basically get RF tones at the repetition rate of the laser, but we see these spurs underneath it, which are basically related to this sort of periodic timing jitter. And so this is a very subtle effect, but this is the kind of concept that literally determines your overall timing jitter and the amplitude noise performance of the laser. Here we take a look at the top part of the pulses, and also we see amplitude jitter. And this is something that inherently will happen in a harmonically mode-locked laser, and that's something that we want to get rid of. So a couple of more cartoons to kind of drive the point home. Here we have a standard mode-locked laser. I'm going to have one pulse in the cavity. I'm going to modulate the gain at the round-trip time. So basically, our modes here are basically, C over L. If I'm going to run the laser at 10 gigahertz, this is a very, very, very tiny cavity. Pulses come out at 100 picoseconds. If I bang a photodetector, I'm going to see an RF power spectra shown here where we have peaks on a 10 gigahertz grid. There are these sort of noise sidebands shown here. Amplitude noise sidebands are flat with respect to harmonic number. Phase noise sidebands increase with harmonic number squared. The thing I want to point out is let's take a look at the phase noise, or the noise spectrum right here. So we're going to zoom in here, and so now we're showing a single sideband noise plot. This delta function here is referenced at 0 dBm. These noise plateaus may be down at around minus 120, minus 130, minus 140 dBc per hertz. The system noise floors are basically related to shot noise or measurement noise, maybe down at around minus 160 or 170 dBc per hertz. But the important thing is the timing jitter and amplitude noise is related to the area under the curve. And so it turns out with this kind of a laser, where the axial mode line widths are not super narrow, it produces a corner frequency in your phase noise plot, which is at large offset. And so ultimately, this determines the overall noise. That is not a good feature. If we could somehow make the cavity longer, this corner frequency will move in, and your integrated jitter would potentially be lower. So the takeaway message is that this corner frequency will move to larger offsets with short cavities. And so that is a problem when you want to do high rep rate lasers. So now, here's the concept of doing high rep rate lasers with an extended cavity. Here I have many, many pulses in the cavity. Again, let's say we're modulating the gain at 10 gigahertz. And let's say the cavity fiber length is a 10 megahertz cavity. So I've got 1,000 pulses in the cavity. And notice I've purposely placed these pulses around the cavity so they don't really look uniformly placed. That's the result of the supermode noise. These pulses are sort of not quite randomly placed, but they're not perfectly on a perfect temporal grid. Now, each one of these pulses generates an axial mode grouping, and these things compete with each other. Notice that there are two important frequency parameters I'm trying to talk about. One is basically the mode locking rate, 10 gigahertz, and the other one is the cavity mode spacing, 10 megahertz. And these different groupings compete with each other. When I bang a photodetector, again, I get out the standard RF tones at the repetition rate of the laser, 10 gigahertz, 20 gigahertz, 30 gigahertz, etc. But the mode beatings in here create those spurs or supermode spurs, which, when you take a look at the single sideband phase noise, you get the standard plateau and a roll-off, but you get all of these different spurs which go out to the Nyquist frequency or half the repetition rate of the laser. So when people show you harmonic mode lock lasers and basically stop the plot here, boom, and say, wow, look, great jitter, well, they're hiding the dust or dirt under the rug. Because when you bang a photodetector, these electrical components contribute to the timing jitter. And so to see this, you have to have phase noise plots that go out to the Nyquist frequency of 5 gigahertz. It turns out now that the energy in each one of these spurs is equal to the energy here. So while you think you have low noise here, you're going to have, n number of supermode spurs. And remember, the jitter goes as the square root of the area under the curve. So basically, your jitter is basically, n times the area under that curve. And so that's not good. But notice, by having the longer cavity, this corner frequency moved in. And if there was some way to get rid of this, we'd have a good low jitter laser source. That's the trick. Somehow push this thing in, get rid of those. This corner frequency is related to the axial mode line width of the laser. So if you can somehow manage to make the line width of your axial modes narrower, you're going to do great. How do you typically do that? You either make the loss less, or you make the reflectivities of your mirror higher. So we can make the world's best mode lock laser by having 100% mirrors on the front and back part of the cavity. And this is great, but you can't get any light out of the cavity. So that's a hard problem. So the trick we came up with, and it's been around for a while, is to basically drop in a high finesse, ultra low expansion quartz etalon or filter, it's just another laser cavity, into this fiberized cavity such that the round trip time matches the mode locking rate. So here we put in an etalon in the cavity where the free spectral range is 10 gigahertz. And so with a 10 gigahertz filter in here, it selects out axial modes on a 10 gigahertz grid. And then we're just selecting one axial mode group where the modulation information from one comb is shared with the other. And then we have a complete coherent optical frequency comb. It's on a 10 gigahertz grid. But remember that the line width of an axial mode is going to be related to this fiber length. So we're able to get wide mode spacing and narrow comb line width here, generating an extremely good low noise laser. So if you don't like that sort of time domain, here's a frequency domain description. You know, I could have said in the time domain description that one pulse basically comes into this etalon and it rattles around, and in one round trip the next pulse comes in, so what was left is now shared with the next guy. So you choose a photon lifetime of this proportional to one full round trip. So when one pulse comes in this cavity, as it's ringing, it's effectively sharing energy with every single pulse, generating coherence or correlation between the optical pulses. So if you don't like the time domain description, here is the frequency domain description. Here I've just overlaid the Airy function of two Fabry-Perot cavities. Both cavities have reflectivities on the order of 90%, 10% output coupling, and I've chosen a ratio of free spectral ranges to be on the order of 8. So that basically means that the dotted curve will basically pass by 8 axial modes before it repeats again. Now, when these two nested cavities are multiplied together, this is what I get out. And so notice that I wind up maintaining the narrow line width associated with the long optical cavity. That's basically the narrow free spectral range, or long cavity. And I maintain the wide spacing associated with the 10 gigahertz cavity, if you will. So the 10 gigahertz cavity is sort of the dotted line. The fiber cavity is sort of the solid line. And when you put these two things together, this is what I get. Now, remember here, the output coupler is 10% on both of these things. And if I were to try to reproduce this type of curve with a single cavity, the reflectivities would have to be 99%. So in this kind of nested cavity approach, I'm able to get 10% of the output power. With a regular fundamentally mode lock laser, I'll only be able to get 1% of the power. So this is the trick. I can build a laser that looks like I've got 99% reflectors, but actually get 10% of the light out by using this nested cavity approach. That's a nice little trick. Here we go. Okay. And if it's still not clear, we've got another example. Here's my mode lock laser, a cartoon. Here's gain. Here's an isolator. It's unidirectional. Here's my Mach-Zehnder modulator. There's some DCF to compensate for the dispersion. I'm going to modulate the gain at 10 gigahertz. So this distance here is related to the mode spacing associated with the cavity, maybe 10 megahertz. And I'm going to modulate the gain at 10 gigahertz. I'm going to take information from this red comb, and I'm going to share it with this guy and share it with that guy. But remember, this also sees the same modulation and shares it with this guy and the next guy. And that gives us the supermode noise, which we hate. Now, when we drop in an etalon, the etalon transmission function is shown here. Notice it effectively selects only one mode group that we wish to have. When you multiply those two things together, we wind up obtaining the wide mode spacing that we want for high repetition rate, but the narrow line width associated with the long storage time, or cavity Q, that we're looking for. Now, in order to really make this thing work for sure, you had better make sure you stabilize this optical fiber so that the modes associated with the fiber stay locked with respect to the modes associated with the etalon. That is a key trick. So here's one version of the mode lock laser. We just use a commercially available semiconductor optical amplifier. We have a couple of isolators to force unidirectional operation. We have a sealed ultra-low expansion quartz etalon. These things are really secondary optical standards, so they're very, very good. We couple in and out of this device here. The effective insertion loss is less than a dB. It's got curved mirrors. The free spectral range is 10.287 to match nominally a 10 gigahertz mode lock repetition rate. We modulate the gain or loss in the cavity with a standard lithium niobate modulator. This is just a standard variable optical delay to kind of tweak the cavity to be close with respect to resonance here. And then we do our phase lock loop. So our phase lock loop is nothing more than a simple Pound-Drever Hall concept, but we're doing Pound-Drever Hall intracavity. Normally, Pound-Drever Hall is a concept where you take a laser and you lock it to a reference etalon that sits outside the cavity. Here, our etalon sits inside the cavity. We said, gee, if we have an etalon, a -S etalon, why can't we just lock to that thing directly? So we do. And so the way we do this, we tap a little bit of the light out, shown here. We put it through a phase modulator. This puts phase modulation sidebands on each and every single frequency comb component. We take that light and we re-inject it back into the cavity. The phase modulation sidebands are not resonant with the etalon. They bounce off of that cavity, and based upon whether the axial modes of the mode lock laser are close to resonance with respect to the etalon or not, we take the reflected phase modulated sidebands, we bang a photodetector, we take a photodetector and put it into a mixer, and we mix it with a piece of a sine wave signal that was used to put the phase modulation sidebands on the combs. We mix this thing in quadrature. That generates an error signal which is effectively differential in nature, which tells us not only how far our frequency combs are off with respect to the etalon, but it also tells us which direction to push the fiber. We take that error signal, we put it into a proportional integral differential controller, and we put that on an optical fiber phase shifter, just fiber wrapped around a little piezo, if you will. That's how we make this thing. Someone asked me, gee, Pete, this is great. Sounds like it's on a 100-foot optical table. What does it look like? So here it is. It's in basically a 16 by 16-inch box. There are the 1-inch holes. All of the cables come in and out of the box here. We take very special care to make the box very quiet. We have thermally isolating foam, acoustically isolating foam, and we put a lid on this thing when we run it. The etalon is, in fact, a sealed etalon. The effective finesse is 1,000. Here's a picture inside the box. The etalon is basically shown here. That is the only free space component that we have in the laser system. All of the components are commercially available, so you can actually go out and buy the components and build one of these things. Let's see what comes out of the laser. So here's just mode-locked optical pulse trains coming out on a sampling oscilloscope. This is not averaged. No, so you can see how clean these things look. The pulses come out of the laser chirped, about 15 picoseconds. We can pass them through either some dispersion compensating fiber or dual grading compressor. The pulses are compressed down to about a picosecond, which is close to the transform limit of this particular output spectrum. Here's the output spectrum that we see running right at C-band. Each one of these dark lines is an optical frequency comb. If we go in and take a careful look at one of these things, here's what the optical signal to noise characteristic looks like on a single comb component. This was measured with, I think, an Agilent high-res OSA. And if you ever use one of these things, there are sort of little sidebands on the local oscillator inside the Agilent. That's what those things are. So we're basically showing better than 75 dB optical signal to noise on a single comb component. These combs, again, are separated on the order of 10 gigahertz, and we have maybe on the order of 160 or 200 optical frequency combs. Full bandwidth here is about 8 nanometers. So this is a super duper great comb source. Yes, sir. Yes, sir. Please. And everyone, please feel free to ask questions. Yes, sir. Let's go back. Oops. Yes. Yes. couple of reasons. First thing, when you do semiconductor lasers, in general, semiconductor lasers typically do not like to have sub-picosecond pulses propagating through the gain due to all sorts of, non-equilibrium gain dynamics. And so as a result, when that happens, that tends to provide much, much less gain. And so if you have nonlinearities in the system, like a saturable absorber, it may make it more difficult to have good efficient modulation by the saturable absorber. This is, in fact, an actively mode-locked laser, so you might say, we really don't care. Now, the flip side is that since it's actively mode-locked, it's particularly better to let the pulse run chirped, because it's going to feel that modulation window of the modulator much more efficiently, and the laser is going to want to track the modulation signal as compared to when the pulse is super short, and then it's sort of sitting, at the flat part of the top of the transmission of the sine wave. So there, you could have much more timing jitter. Whereas when the pulse is a little fatter, it's going to feel the windows, the edges of the temporal window that's opened in the modulator. So it is better for us, we believe, to let the laser run in that sort of chirped regime. And again, the second feature was you get more energy out of the laser because you don't have to deal with the short pulse gain compression effect. Yes, sir.
The length of the cavity,
Yes.
the microwave oscillator you have being the active mode locking, that's not tied into this feedback loop at all?
And so we're using a Poseidon Oscillator in these particular experiments. Poseidon Oscillator is pretty good. Let me say a couple of features also. Even if we were to just slave it to an Agilent, yes, the lasers are sort of tracking and following the oscillator. It turns out that when we started doing these measurements, the laser itself filters the RF noise. And so in many instances, when you go to measure noise, if you're using a very, very lousy synthesizer or oscillator, the laser will have lower timing jitter than your synthesizer. And so when you measure the noise in a mixer, at some point you're going to be measuring laser noise, and at some point the laser noise drops below the noise of your synthesizer, and then what's coming out of the mixer is basically the noise of your noisy synthesizer. And so it doesn't make your noise plots look really good. So we've basically gone to a Poseidon just because that has extremely good low noise at high offset. So we don't do anything in terms of trying to go back and tweak the oscillator because for us it is literally the secondary optical reference, the Etalon, which has much better timing stability than any other kind of electrical oscillator we can build. And so we will let the laser drift at low frequency with respect to the oscillator. And a Poseidon generally is halfway decent. Some of these things I think will become apparent maybe in the next couple of view graphs. So here is basically the single sideband phase noise of this particular laser. There's the AM noise. The takeaway message from the AM noise is while you do see a bunch of line noise, the AM noise is basically noise floor limited at about 0.02%. And we just can't do any better than that. And we're measuring this with the Agilent carrier noise test system. And so basically, in the carrier noise test system, you just put one port in for the AM noise, and for the phase noise, you have to mix the Poseidon with your photodetector current. And so the Agilent carrier noise system does that for you. I mean, if you wanted to build your own system, then it would be having your own mixer and either putting them in quadrature or in phase to get amplitude or phase. When you put them in quadrature, yes, there is amplitude noise, but the amplitude noise is suppressed on the order of 20, 25 dB. So then you're pretty comfortable in saying, aha, the noise that we see here is primarily due to phase noise. But this is the classic, Agilent 5505 carrier noise test system. So the thing I wanted to say here is, again, notice there's a nice corner frequency here at around 100 kilohertz or so. When we did mode lock lasers directly at 10 gigahertz, this corner frequency is way out here at a couple of hundred megahertz, and the noise plateau was a lot higher. And so by these novel engineered cavities, you can suppress this white noise plateau primarily due to spontaneous emission. You push the knee in due to the long length, and you might look here and say, aha, look, those might be evidences of supermode spurs associated with the long fiber cavity. But these things are now being suppressed below the noise floor. If you could really get below, 170, 180, this thing would drop down and you'd sort of start to see little spurs all the way going out to Nyquist. But those things will always be there. Mathematically, they must be there. But they're below the noise floor. So AM noise is measurement limited. The integrated phase noise, now I'm showing you, I'm integrating from 1 hertz out to 100 megahertz. It says it's like 3 femtoseconds. But really, what you really want to do is you want to integrate from here in. And really what you want to do is you want to start out at 5 gigahertz and integrate in. And we built carrier noise test systems that went out to 5 gigahertz to basically show there were no supermode spurs. We couldn't get as good a low noise floor. And so we are very comfortable now just showing you offsets out to 100 megahertz because we know what exists and what doesn't exist out here. Integrated jitter to 3 femtoseconds from 1 hertz to 100 megahertz. Integrating shot noise out to Nyquist is about 14 femtoseconds. Note the overall dynamic range is about 10 to the 16. Okay, so now we wanted to measure the line width of one axial mode. So we took a commercially available laser, this is from Orbitz, and we did some simple heterodyne beating. So we mix this with an Orbitz, we bang a photodetector, we take a look at the RF spectrum, and so we take a look here. This is the effective beat note. The beat note has a line width of about 500 hertz. So this is a pretty good frequency comb. Hundreds of combs on a 10 gigahertz grid, right in C-band, over 75 dB optical signal to noise with a line width of like 500 hertz. Now a Menlo, that's Ted Hensch's company, he got the Nobel Prize for doing frequency combs. A Menlo system has a line width of about maybe a megahertz. So this is substantially better. It's semiconductor diode based, so all of us semiconductor diode laser guys can say, yes, we can have better stability than a Menlo. At least that's what we do in our lab to some degree. And then we took a look at the overall long-term stability. Long-term stability is around 150 kilohertz measured over half a minute. But now, this number here is basically determined by the stability of the CW laser, the orbit. So we really still don't know how stable the fluctuation of the comb is. And so this is really still pretty good. We think it is, anyway. Okay, now we all know what we all know from our laser classes, what determines the line width of a laser. So shallow towns, we think about loss, we think about power, all of those things. So we talked about, line width of the laser, making the cavity long, narrow line width. So now I want to talk about the effective intercavity power. So what we're going to use here is something called a Slab coupled optical waveguide amplifier. These things produce significant power. So they're semiconductor optical amplifiers which have an extremely small confinement factor. So the mode is quite big. You can couple lots of power into an optical fiber because the mode is round almost. But notice that the overlap between the optical mode and the quantum modes is very small. So with the small confinement factor, you can have extremely high output saturation powers. We're using devices which can have PSATs on the order of 300, 400 milliwatts. And we get these things from Lincoln Labs. They actually have devices which have output powers of about a watt. And so this is pretty good. Low confinement, they're long, about 1 centimeter. Yes, you have to drive it with a lot of current, like 5 amps. But again, you can couple a lot of light into an optical fiber. Boom. So we built the laser, except we're just using a Scour, unidirectional, same kind of etalon. No magic, no magic there. Oops. Here we go. And there's our phase lock loop to standard intracavity boundary for Hall concept. I just want to start to show you some resulting data. Here's a picture of the sealed ultra-low expansion quartz etalon. We buy these things from Advanced Thin Films in Boulder, Colorado. This one has finesse of about 1,000. The particular spectrum I'm showing you here, notice has a different shape than the squarish one. To get the squarish shaped spectrum with nominally uniform power per comb requires dispersion compensation. So we have a piece of DCF in the cavity. This is just purely anomalous fiber. We see the frequency combs. Here's a clean RF tone. Similar optical signal to noise. It was just basically related to power on the photodetector. And here's a single sideband phase noise. What I want to point the audience's attention to is this red line here. This is basically the absolute noise of the Poseidon Oscillator that we use to mode lock the laser. So in this regime, from here in, what we're measuring on the blue line is basically residual noise because it's the excess noise related to the Poseidon. From this point here, since the measured data is higher than that of the Poseidon, we're measuring absolute noise. So the blue curve is a representation of both residual phase noise and absolute phase noise. And so the absolute noise would basically go from here to here and up. But the key feature is we just want to show you how robust this operation is. And again, the effective relative jitter. Notice now we're integrating from 100 megahertz in. And so this stuff here is just shot noise. And so notice, as soon as you come in, boom, the integrated area just skyrockets up and basically saturates and doesn't really get much higher than this level here. So it's somewhere around, maybe 1 3/4 femtosecond timing jitter. So the key feature is to recognize is that your timing jitter is really limited to shot noise. This stuff under here is really not contributing to the timing jitter whatsoever. So that's an important feature. Now, there is technology out there that will allow us to push this much further down. And so at that point, we hope to get to a point where the integrated jitter, due to shot and thermal noise, we can push down to maybe minus 183. That shouldn't contribute much. And then hopefully, we'll then be limited to the jitter, to the technical noise here. We'll have to get there to see if we can actually do that. Pulses are about just slightly under a picosecond. Closer to the transform limit with better than 90 dB dynamic range. Okay, so now we took this mode lock laser and we used it in a MOPA configuration. So we have a scour inside the cavity. And so great, take our mode lock pulses and pass it through a scour on the output. And so what we're just showing you here are gain plots versus output power, the kind of classic plots here. And what we're showing you here that we're able to get close to 400 milliwatts of output optical power on a 10 gigahertz mode lock laser. And these are the spectra directly from the laser and output spectra with different output powers depending upon the bias on the power amplifier. Notice there is not any real significant degradation in the output spectra here. However, the caveat that I'd like to point out, which you may not recognize, again, the laser pulses coming out of the pulses coming out of the laser are chirped, so we're passing stretched pulses through the amplifier, 10, 15 picoseconds. So the nonlinear distortions that you would normally see are suppressed. We do have results which show what the output spectra would look like if we took compressed pulses of sub-picosecond and passed it through the scour. And in fact, you will get the classic nonlinear distortions that we've measured many years ago in mode-locked MOPA configurations. And so this translates to about 5 milliwatts of power per comb line. And so this would be really great for any kind of classic WDM where you want milliwatts of power with hundreds of lines from a single simple source with just one sort of locking element. One locking element, one heating element, one current source. And so we think it's a pretty good thing. Let's try this. Oh, there it is. Let me make sure I didn't miss anything. Okay, so now what I want to point here is to show you the benefit of the fact that this scour has 300 milliwatts intracavity. And that should help with the line width. Not only should it help with the line width, if it helps with the line width, it's going to help with respect to the integrated jitter. So there's a bunch of plots here. The black is just the noise floor. What I'd want to point out is the red plot and the blue plot. The red plot is basically the all anomalous fiber cavity with the standard commercially available Covega device, shown in red. Let's compare that to the just recently shown data of the all anomalous cavity with the scour, shown in blue. Notice that there's nominally a 10 dB reduction in phase noise almost across the entire measurement window. So this really clearly shows you the benefit of having higher intracavity power and making these low noise lasers. Now, let me talk about an arc sine phase modulator, which can be a true linear intensity modulator, but also this is going to be a device that allows you the ability to select a single frequency comb component from your mode lock laser and perform modulation and eventually detection. So just very quickly, we all know what modulators we want to have: large bandwidth. We want this thing to be linear. We want it to be low V pi. We want it to be able to handle good power. And if you can somehow have a modulator that can filter at the same time and make arrays, that'd be great. Not only that, but normally modulators have an insertion loss. Boy, I'd love to make that negative, meaning I'd like to put light in my modulator and have it come out brighter at the back end. So that's what I call negative insertion loss. And so the classic concepts for modulating are directly modulating a laser diode that gives frequency chirp. You can have external modulators like lithium niobate. That has a nonlinear modulation transfer function. This is the kind of stuff I want you to focus on. It has relatively high V-pi. Electroabsorptions are okay, but they can't handle a lot of power. And so we're going to propose our concept for modulating frequency combs is a concept of injection locking of or some sort of resonant cavity with gain. Resonant cavity with gain is a laser. So we're going to do it with a VCSEL. I'm going to show you that this produces arc-sine phase modulation. And if I take an arc-sine phase modulator and I put it into a Mach-Zehnder configuration, I will get an interferometer which is truly linear, but more importantly, because it's interferometric, we can get large contrast. And that's something that's very typically hard to get in the classic lithium niobate or electroabsorption modulator. So the concept is shown here in my simple cartoon. Master laser injection locks a slave. Here's a slave laser just running at omega naught. I come in with the master laser. It injection locks this. The slave now switches to this new frequency. This concept has been studied extensively with circuit theory back in the late 30s or early 40s by Bob Adler. And it turns out that the output frequency is the same as the input here, but it picks up a phase difference, and that phase difference is proportional to the frequency detuning, or how far this frequency is away from that guy. So the phase is arc-sine of the frequency detuning, reference to the master laser frequency. So here's a cartoon. What I'm showing you here in this dotted line is sort of the locking range. This red arrow here is a slave laser running in its free running state. The blue arrow is basically the master laser running here. This distance is the frequency detuning. This curve here is arc-sine. So the output color here is basically this phase. This is plus pi by 2, and that's minus pi by 2. So now the trick is there some way I can modulate the free-running cavity resonance of the VCSEL, maybe perhaps by modulating the current in some way? And if you do, the free-running frequency moves back and forth, but notice the intersection point rides up and down on this arc-sine curve. So by doing this, I'm getting an output light, which is now modulated in phase, but the phase is arc-sine of this frequency detuning, or potentially arc-sine of the driving current. If you still don't understand, so now the benefit is that here's classic Mach-Zehnder. The output goes as a 1 plus cosine over 2. There's the transfer function. If I drive this thing with ramps, I get out a sine wave on the output. So if I had an electrical signal like a ramp which is rich in Fourier components, what came out was a simple sine wave. I've completely destroyed the signal. Whereas in this particular case, the arc-sine cancels the 1 plus this cosine function here, and now I get a transfer function which is perfectly linear. This is also interferometric in nature, so I get large contrast. So when I drive this device with ramps, I get ramps on the output. So this becomes what we believe is sort of the first, interferometric modulator which has a true linear transfer function, if you will. Now, if you think that's cool, because I thought it was pretty cool, because 1 plus cosine for an interferometer has been around since, a million years, and Bob Adler's stuff in circuit theory has been around since the late 30s. We just got lucky and just saw how these things worked together. There were some papers in the late 80s where a guy wrote this theory and he says, 1 plus cosine of the arcsine, and this is messy, so let's just linearize it. I'm like, oh, he missed it. He missed it. So anyway, so get a load of this. If I have a bunch of frequency combs now coming into the VCSEL, what I'm going to do is I'm going to adjust the DC current of the VCSEL. And we all know that with a little bit of heating or DC current, the VCSEL will tune. So I'm going to tune the VCSEL so it's going to be within the locking neighborhood of this red frequency comb component. I'm going to shine all the frequency comb components on this guy, but I'm going to bleed in a little bit of small AC modulation. And that power spectrum of the modulation I'm going to show here in my cartoon. And so when I do that, what comes out is just the red frequency comb component with the modulation sidebands of F1 on it. The other guys basically come out with no modulation on it whatsoever. So this device serves as a phase modulator and a filter all at once. So you can do sort of channel selection at the same time. by just adjusting the DC current, tuning the VCSEL to a different comb component with different modulation sidebands here, I'm able to get out a blue frequency comb component modulated without doing any modulation of the red comb component. This is just a tuning curve. And here is just the effective result. We have a CW laser. We split it. We build a Mach Zender. We have a little circulator here. We injection lock a VCSEL. This is my DC current. I can put in 1 or 2 tones. We're going to look at 2 tones for SFDR measurement in a moment. We take the output light. We can bang a photodetector, looking at spectrum, photodetection, and we actually build a little loop to stabilize this fiber cavity to ensure that this thing stays in quadrature, if you will. We don't want the fiber lengths mixing because that will give you residual AM modulation. Okay, here's the static arc sine AC modulation response. This is a commercially available VCSEL that we bought from Raycan. This shows we can have modulation speeds out to about 5 gigahertz. And the effective current that we're using to make this happen is on the order of tens of microamps, and that translates to a VPi of just a few millivolts. And we did a 2-tone SFDR measurement with a laser that has a noise floor of around minus 160 dB. So it sort of suggests we could potentially have, in this case, an SFDR of about 130 dB hertz, 2/3. Now, the limitation of this is that, in fact, when you modulate the current here, you're modulating the carrier density or index. And we know the mode spacing is C over, NL. And so N is in the denominator. So that is not linear. It's 1 over, if you will. That's one limitation. The other key limitation is that the VCSEL is a cavity. And you'll say, arc sine for a cavity. That's not right. Any cavity has an arc tangent phase response. And I said, that's absolutely right. And that's when the cavity is passive. So when you injection lock a cavity with more and more injection power, the phase response starts to adiabatically evolve from arc sine to arc tangent. So you have to be able to tickle this with very, very small injection powers. 10 to the minus 3 is about a very, very good place or less. Okay, now I want to talk about injection locking VCSELs for detection. And we're just going to, operate on the concept that we can measure a voltage change, and the change across PN junction is basically due to change in carrier density. So let me explain what the heck is going on here. Here's my sort of phase response of a VCSEL. There's the locking neighborhood. Here's the arc sine phase. And if I'm basically injection locking here, I can measure a voltage. So far, so good? Great. Now, if I come in with a slightly different frequency, let's make it bluer, we all know that the slave laser now oscillates on the blue. But I did nothing with respect to the current. How the heck does the laser manage to move to the blue? The only way that happens, somehow effectively, the cavity length must have gotten shorter. Well, it didn't get shorter. I didn't move any mirrors. The only way that can happen is that somehow the index had to go down. The only way the index goes down is if the carrier density goes up. It's a plasma effect. Carrier density goes up, the voltage goes up. Similarly, if I injection lock on the red side, I measure a reduction in voltage. Great. And so now we can put this concept again using VCSELs as a channel filter also. So I can have phase modulated signals coming in here. And what I'm going to do is I'm going to tune the VCSEL to one particular comb component which has phase modulation on it here. This is analog modulation, so let's kind of do that. And when I do that, boom, I'm able to measure a voltage where the voltage response is proportional to the information that's on these side modes or this comb component. If I change the DC current to the VCSEL so that it's resonant with channel 2, and I tune the VCSEL over here, boom, I'm able to detect this information sidebands and see nothing else. So we tried this concept very simply. I took a CW laser. I intensity modulated it just to get 3 tones, tone 1, tone 2, tone 3. I just chose 3 simple lithium niobate modulators and put simple analog phase modulation sidebands on it, 800 megahertz, 900 megahertz, a gigahertz. I combine them. I shine them all on the VCSEL. Here's the optical spectrum of the VCSEL, and here's the optical spectrum of the 3 different comb lines with 800, 900, and a gigahertz modulation on it. And I'm going to tune the DC current of the VCSEL to be resonant with either channel 1, channel 2, or channel 3. And the results are shown here. Here is the result where the VCSEL is resonant with channel 1, and we're able to pick up the 800 megahertz modulation with 60 dB of signal to noise. Notice there's nothing else at 900 megahertz or a gigahertz. We can see the tuning the VCSEL to 900 megahertz and a gigahertz. We're able to receive the signals without any other corruption from the other modulated tones, even though they're all hitting the VCSEL at the same time. So this is kind of a cool concept. And I'm going to bring all of that together in a view graph. I think it's after this. But now I want to plant a seed and say, well, gee, Pete, this kind of injection locking stuff is great for CW light, but you know, we know you're a pulse laser guy, and so how do you basically make this linear modulator for perhaps optical sampling in a photonic ADC system? You know, an input pulse train is not a single axial mode component, but has many frequency comb components. And I say that's great, that's correct. So what you do is you build a Mach Zender where the laser is not like a VCSEL, but maybe a Fabry-Perot, and you choose the mode spacing here to match the mode spacing of your frequency comb laser. So in that particular case, the axial modes of your mode lock laser will injection lock, if you will, every single resonance of the Fabry-Perot. So when you modulate the current in the Fabry-Perot, oops, did that work? Crap, hold on. I'm trying to get this cartoon to go. Nice and easy. There it is. Yeah. So notice all the comb lines see the same effective arc sine modulation. So when it's combined together, I get out perfect linear sampling on the output. Okay. Let's start to talk about applications. How am I doing for time? Okay. Okay, very quickly. Yes, sir. No, we haven't. You know, we're actually trying to build this device. And so the challenge with building this device is that our combs are very linearly spaced, and the Fabry-Perot device has dispersion in it. So basically the comb spacings will walk off if you're not, you have to sort of take that into consideration. So there's going to be a limit to things like sample rate, things of that nature. And so that is a problem. Dispersion, so that's another message. Dispersion is just something that you have to really be careful with frequency combs and how you want to do things. Okay, so heterodyne detection, we basically, it's useful for our ability to basically make, if we can make arbitrary waveforms, the concept is how do we effectively measure them? And so the concept is shown here. We basically have two frequency comb sources, and you basically bang them on a photodetector. What I'm showing you here is a frequency spectrum of mode lock laser 1 and a frequency spectrum of mode lock laser 2. They do not have to be the same repetition rate, nor do I need to know anything about either sources. The key feature is that I take a look at the beat note generated by these two, the beat notes generated by these two, the beat notes generated by these two. They will show up in the RF power spectrum. And if you do this right with the proper offset frequencies and detunings, we will generate in the RF power spectrum a representation of the optical frequencies of your mode lock laser. And so then by banging a photodetector, you can physically see on a slow scope what the actual pulse and carrier frequency looks like. So here we did this with a Menlo system. There's the spectrum shown in black. That's a 250 megahertz laser. Here's a frequency comb laser with 10 gigahertz. Notice this is generates mirror image spectra of the frequency comb source. This RF domain. We do a close-up here. Each one of these RF tones is a beat note from one of the combs of our 10 gigahertz laser and the Menlo. And if we take a look on a simple slow scope, notice a time scale, megahertz. We basically generate the optical pulse shown here. Here's a compressed pulse. Here's a stretch pulse. There is something wiggling in here. This is not the actual optical carrier, but it represents the rate of change of the optical carrier, or the chirp that's impressed upon the laser. So you can literally, with a megahertz scope, see femtosecond pulses and see the chirp directly with this technique. This is very nice. This is super stretch where we almost fill the time window. But again, just by playing around with dispersion, you're able to recover the pulses. So if you don't believe that, we took a separate case where we took a CW laser, put phase modulation on it. That's something where we know the phase of. We're going to beat it against the Menlo laser system, and we're going to characterize. This is basically a shot of the raw time domain waveform stuff. What we're plotting here is the instantaneous frequency, or chirp from phase modulation, from this signal here. We Fourier transform this. This is the spectrum that we get in black. The red is the phase, and I've drawn a solid red line to effectively as an aid to the eye to show you what the phase is. And you'll all recognize that in any phase modulated signal, not only do you get a multiplicity of periodic tones, but the phase is flat to one side and the phase alternates 0 pi on the other side. So clearly we're able to recover the magnitude and phase of an arbitrary signal. Okay, so now waveform generation. This is the concept of taking individual axial modes and manipulating the amplitudes and phase to generate a time domain-based waveform. If things are static here, your waveform is periodic. What we want to do is basically have our comb source and put independent arbitrary modulation on these combs so we can have arbitrary waveforms of infinite temporal extent. Notice the instantaneous bandwidth is just proportional to the full optical bandwidth, but all I need is modulation, modulators with speeds proportional to the comb spacing, 5 or 10 gigahertz. So we can get arbitrary waveforms with instantaneous bandwidth of several terahertz using 5 or 10 gigahertz electronics. That is, in fact, a very nice feature. How do people do waveform generation? They take a frequency comb source, they separate out the frequency combs, and they go into a liquid crystal spatial light modulator. Those things are slow. Well, great. Since we now have some ability to modulate comb lines and filter directly, like VCSELs, let's use it. Notice that when you injection lock with microwatts of power, milliwatts of power come back. So in fact, I do have negative insertion loss or gain in the system. Now, these things can be modulated at 5 gigahertz. That's what we're showing. But the most important thing is with gigahertz modulation speeds, liquid crystals typically go at best kilohertz. So this is sort of, a million times better. Not only that, as you know, these things can be fabricated in 2D arrays with channel counts of thousands. So you could literally make a 32 by 32 VCSEL array, with milliwatts of current, maybe an amp or so of power, and basically do arbitrary waveform generation with 1,000 channel counts. And I just don't think it's harder to do that with an arrayed waveguide grading router with 1,000 channels. I think it's just very, very hard. Maybe not impossible, but I think it's hard. Okay, so what we did was we took a comb source with 4 or 5 channels. These things represent our VCSEL modulators. We injection lock a VCSEL and we modulate. And we're going to take a look at what comes out. Here's our simple comb source, just 4 or 5 lines. This is at 6.25 gigahertz. The pulses are transform limited, about 30 picoseconds in duration, separated by 166 picoseconds. We used an Essex virtually image phased array device to separate out the individual comb components to allow us to inject the VCSEL modulators. Here's a transmission characteristic of one of the windows or passbands of the VIPA device. And here are some generated waveforms. This is on a slow modulation where we're taking the 4 channels and modulating them at 4 megahertz, 5 megahertz, 6 megahertz, 7 megahertz. These are just snapshots of different waveforms. I'd like to point at this point here. Each one of these different lines is a pulse, but if we take this piece here and look, this is what the pulse train looks like. If we go right here, this is what the pulse train looks like. If you go right here, this is what the pulse train looks like. And notice that the pulses basically look different. So it's evolving on this sort of microsecond time scale. Now, we put this concept on steroids. Again, here's the pulse train running at 166 megahertz. Here's our 4 comb lines. Now we're modulating at 700 megahertz, 1.5 gigs, 2.3 gigs, 3.125 gigs. This is half the repetition rate. Here's the optical spectrum shown here. Here's the input pulse train. Here's the output pulse train. Here's the output pulse train on the same scale. So what you want to take a look at is that this pulse here is this shape. This pulse here is this shape. This pulse here is this shape, and so on. So clearly this is showing you, with this injection-locked VCSEL approach, you can do pulse shaping at the repetition rate of the laser in a very compact format. So we are just about done. This is the concept I wanted to talk about before, this concept of using injection-locked VCSELs for detection, etc. So here might be a concept for a cross-connect switch. I have a coded OCDMA pulse here, or whatever it is. It's just something. I have a 1/n split. I'm going to have all the comb lines on 4 detectors. This detector is DC tuned to the green comb line, blue is to blue, etc., etc. This is just O to E to O. What comes out is the black line, which is the current, which is dot dash. This is dot dash double dot, etc. What I have coming in here is an unmodulated mode-locked pulse train. So what comes in here are unmodulated frequency combs. This is a spectral disperser like an AWG, whatever it is. This injection locks a VCSEL, and I take the current and modulate this. The comb line comes out with the red color being modulated with the information from the green comb line. So now the feature is these things can be modulated and changed at close to gigahertz rates. So I hope that it suggests that there is the potential to do some kind of large-scale cross-connect switch, 32 by 32 VCSEL array, 1,000-port channel, something that looks like this, where we can swap or do code hopping at the repetition rate of the laser. That might be something that's interesting. Okay. Boom. And so the last cartoon, there we go. I just want to talk about a concept for CDMA. It's basically corrupting a mode-locked laser pulse so it looks like a noise burst. And the problem is if you want to detect it with photodetectors, a detector at the bit rate is not going to tell the difference between a short compressed pulse or properly decoded pulse or an uncoded pulse. And so we want to come up with a linear technique without using nonlinear optics to allow us to detect coded pulses in an OCDMA kind of network. So the concept is very simple. We just have two pulse shapers, but the concept is really in the detection scheme. So let me show you that here. So here I have an interferometer, and what I'm going to put in are two comb sets with orthogonal coding. And so when all of the phases are basically the same in an interferometer, which is biased in quadrature, when they interfere, everything comes out this port, nothing comes out this port. I do differential detection, and basically you add up all the comb lines. I'm going to call this thing logic 1 here. Let's take another situation where I have a comb set here, a comb set here. This is orthogonal coding. Notice comb lines which are in phase will come out one port. Comb lines which are out of phase come out this port. Notice the power is the same in both ports. So this is power 2, subtract logic 0. So this is a very simple way that I can use simple linear photodetectors to do code division multiplexing or match filtering using Hadamard coding. Okay, let's let it catch up. Oops, I passed a view graph. So we did this experiment. We're going to use liquid crystal spatial light modulators. Here's my optical frequency comb. Here's the output from the interferometers. We're running through a bunch of codes, and when the codes match, one port goes high, the other port goes low. You take the difference, you get twice the output power. When the codes are orthogonal and they don't match, both powers are about the same, you take the difference, you basically get 0. And so we tried to say, could we quantify this? And please do not take this number too seriously. But if we tried to do some sort of error analysis, like an on, off, and what's the width, this would basically sort of suggest, an error rate of something that's astronomically small. All it basically says is orthogonal coding and using frequency combs gives you the ability to match codes with an extreme degree of sensitivity. So, concluding, hopefully I've been able to make everyone excited, that everyone now wants to, remain in Professor Colgin and Bauer's group, and they're so glad to be ultrafast guys because they think frequency combs are the best. I hope. Right, and not only that, but you can use these things with VCSELs and show interesting kind of functionalities with modulation and detection. As a reminder, the combs are femtosecond jitter class, less than kilohertz line width, a 10 hertz per root hertz frequency noise. This is the lowest noise source at 10G. We showed a linear interferometric modulator with very large spur-free dynamic range, very low Vπ, and phase detection without the use of a local oscillator, and channel filtering with good signal to noise. And hopefully we've shown how we can make frequency combs and them useful for arbitrary waveform generation, arbitrary waveform measurement, and match filtering. So at this point, I'd like to thank John for inviting me here. He's been trying to get me here for the last 2 years. It's finally happened, and it's been an honor for me to share with you some of the exciting things that we're going on in the lab. And of course, I do none of this work. It's always the group. I'm just the money grubber, and these are the guys and gals that make it all work. So thanks a lot for your attention, and hope you enjoyed the talk.
That was a high rate of data transfer.
Yeah.
Other questions for Peter? Yeah, John.
I really enjoyed that. A couple questions.
Yes, sir.
Before the SCAWA, you showed using a commercially packaged SLA.
Yes, sir.
What's the material size? That bulk, wells, dots?
That's wells. That's quantum wells. That's a device from Covega. which I think was like a Mario Dagenet company ultimately at one point, which is now bought by Thor Labs. So you can just open up the Thor Labs catalog and boom, buy one of those puppies. It's fiber coupled in a standard, 8-pin, can or whatever it is, 16-pin can. Pretty straightforward. They're maybe $1,000 a hit, I think, something like that. 50 milliwatts is the output saturation power, something like that. Yes, sir. Please.
Couple questions. Question was, in some of your first combs, you said you did intercavity dispersion compensation.
Yes.
But you end up with a square top.
Yes.
For the optical spectrum.
Yes.
Why would we expect that rather than a Gaussian for completely or for near dispersion control?
Right. Yeah. It turns out that certainly when we make mode lock lasers, well, how about there's a couple of ways I could answer this. There are some effects related to self-similaritons which are going on in the laser, which inherently likes to generate these square spectra. I could approach it that way. Number two, there are some nonlinearities in the semiconductor where the primary nonlinearity related to the gain depletion. So I'm going to draw with my hands. So when the gain depletes like the integral of the pulse, the index changes as a derivative of that. It's like self-phase modulation. So the index change is going to look like the shape of a Gaussian. So that means that frequency tone, look at one color, is going to have a power and it's going to shift this way and shift back. So generally you tend to wind up with spectra which are squarer due to the sloshing back and forth. And so that is one way we can explain it. What we also notice, more importantly, without the DCF, there is this effective roll-off. And so there's a time to wavelength mapping where the pulses coming out wind up with a sharp rise and a very long tail. And so the shape of that spectrum on the log scale is basically the shape of the pulse. So with DCF, we're doing better matching of the optical modes, and so we're able to better match the modes of the fiber cavity and the etalon, so we're able to get more power into it before the modes walk off. Again, dispersion is an important problem in having these nested cavity approaches. Third thing, in my 25 years of doing mode lock lasers, when you really make the laser work well, they do tend to have these squarish spectra. Sometimes they're lopsided, but the edges just tend to, for me, tend to look squarer. John's maybe a much better guy, and the spectra come out Gaussian, and crap, we just don't, they just tend to, when we really, really make it hum well, they just tend to have the squarish spectra. And more importantly, the pulses tend to be extremely compressible. I mean, I can recall taking pulses which were compressed by about a factor of 100, easily getting pulses out which were 20, 25 picoseconds and compressing them to 200 femtoseconds. And the key feature was laser has to run in this sort of very square mode. Please, just keep it coming.
That was my lead up to the follow-up, the final question.
Yes.
Was that, what part of your pulse you get out from most of these cavities is linear dispersion versus cubic versus quadratic dispersion, and how much compensation do you do for each one of those?
Right. So primarily we do quadratic dispersion compensation, whether it's with grading pair. Now, grading pair will in fact introduce a little bit of cubic. We've also done some cubic phase compensation, but it doesn't really buy you much. I mean, the main part of the pulse is going to look clean. The cubic phase is just going to be in the wings. So it really doesn't do a heck of a lot, at the end of the day. So we primarily just do quadratic dispersion. We should be having a paper coming out in the next special issue of JSTQE where we actually use the multi-heterodyne detection concept and look at the phase properties of these mode lock pulses in the several different classes of these frequency comb sources that we build. So look for that in the next couple of months. We just got back to review the other day. So we can make some corrections and it'll come out. Yes, sir. My pleasure.
Other questions?
Yes, sir.
You had somebody back here. Thank you. Me.
Yes, sir.
On the arc-sine modulators, and
Yes.
I guess it's really a general question about the pixels involved within these modulators and also as detector modulators. I didn't quite understand the bandwidth limitations and what you were assuming about the bandwidth or the current linear
Right.
properties.
Correct. So let me say, so this is a device that we bought from a company called Raycan. I think they're in Korea. You can buy these things for $200. They come in a TO5 can. We cut the leads off. We just attach wires. And so there's going to be some limitation just due to physical electrical connections. And I'm sure they're probably not doing anything special with respect to the design of the VCSEL for high-speed modulation. So I'm just assuming that the main sort of roll-off is primarily due to generic carrier dynamics. You know, there is nothing special about these VCSELs, and that's what they spec when you buy them. Usually they'll give you an AC modulation response. They spec it at 4 gigahertz. And so
you're assuming a flat response to some bandwidth, and that's required for
right, we assumed a flat response. But if you notice, there is a if you notice in our plot, there was a part that sort of went up as you went closer in. And that's basically enhanced phase modulation due to the thermal effect. Because at low speeds, you know, you're able to physically change the index in a much more robust way, and the depth of modulation is a lot higher. So those are the things. However, you showed me some beautiful data of VCSELs going to 35 gigahertz and maybe 100 gigahertz. And holy cannoli, you know, it'd be great to have a truly linear, you know, modulator for potential OFDM. Because OFDM now, I think you take a composite signal and they drive a lithium niobate, and there's a lot of signal processing to deal with sort of the nonlinearity of that. You might be able to get rid of that with some of these arc-sine phase modulators and make tons of more money.
Great. All right. There are no more questions? All right. Thank you, Peter.
My pleasure. Ooh, it's warm in here. Woo.
Well done.
Thank you, sir.
I'll take off your.
Yep. Thank you, sir.
Since I
So-
didn't get any time with you yet, I'd
Yes.
like to go.
Absolutely. Okay. So how do I? I'm going to clean up the file. So how do I seal? Oh, I guess I can go to that one there,
Okay.
and that will allow me to see everything.